Welcome to the deep dive. Today, we are taking a massive stack of source material and boiling it down into a single, really breathtaking insight. It's an idea that attacks head-on the biggest problem in physics today.
Absolutely. We're talking about the crisis in cosmology, this fundamental disconnect. Our two main theories, general relativity for gravity and the standard model for particles, they're brilliant, but they just can't explain something like 95% of the universe we actually see.
It's a huge gap.
It really is.
Yeah.
I mean, technically, the models work incredibly well for what they do explain, but they leave these five colossal mysteries just sitting there.
Right. Let's list them out.
Okay, first there's the accelerating expansion of the universe.
Mm-hmm.
We call the cause dark energy, but we don't know what it is.
Number two.
The missing gravity in galaxies. Everywhere we look, galaxies spin too fast for the matter we see. So we invented dark matter. Again, no idea what it is.
Third is the asymmetry problem. Why is there basically only matter left? Where did all the antimatter go after the Big Bang?
Exactly. Fourth, the cosmological constant problem. This one's mind-bending. Theory predicts the energy of empty space should be enormous, like 120 orders of magnitude bigger than what we actually measure. It's the worst prediction in physics history.
And fifth, the Big Bang model itself has these foundational issues, right? Like the initial singularity and why the early universe was so incredibly uniform. We had to invent this inflation field just to smooth things out mathematically.
Pretty much. So, yeah, the standard approach is basically bolting on new stuff. Exotic particles like WIMPs or axions for dark matter, maybe some weird quintessence field for dark energy, the inflation field, all hypothetical fixes for these five huge problems.
But our deep dive today looks at a researcher who says, wait a minute, maybe we don't need any new ingredients. Maybe we just need to look much, much closer at something we already know exists, the quantum vacuum.
That's the focus. We're diving into the work of Professor Dragan Hajdukovic, a researcher affiliated with CERN. He puts forward this single, really powerful idea that might just tackle all five issues in one go.
Okay, so what's the core concept? Lay it on us.
All right, the central hypothesis is this. The fundamental nature of the quantum vacuum, its fluctuations. They aren't just random energy pops. They are virtual gravitational dipoles.
Virtual gravitational dipoles. Okay, wow. We definitely need to unpack that one slowly. This sounds like it gets weird fast. Let's define this sea we're apparently swimming in.
Right. The quantum vacuum, or QV, it's absolutely not empty space in the way we usually think of it. In quantum field theory, they sometimes say nothing is plenty.
Ah, I like that.
It means it's this field present everywhere, constantly buzzing with energy. It's full of these incredibly short-lived virtual particle pairs, saying quark, antiquark, electron, anti-electron, just flickering into and out of existence.
So fast we can't even measure them directly.
Exactly, governed by the uncertainty principle. But they're real enough to have effects.
And we need to remember, this isn't some theoretical abstraction, it's fundamental reality. The analogy used in the sources is great. We're like fish living at the bottom of an ocean, and that ocean is the quantum vacuum.
That's a perfect analogy. If you can magically switch it off, protons and neutrons would likely change mass instantly. Fundamental constants might shift. Chemistry as we know it, gone. It's literally the foundation of our physical existence.
Okay, so this vacuum is buzzing with virtual pairs. How do we get to dipoles?
Let's use a known physics analogy first. Electric polarization. This happens in quantum electrodynamics, QED. If you put a charged particle, say an electron, into this quantum vacuum, it actually creates this tiny kind of non-random halo of virtual electric dipoles around itself.
Okay, wait, let's pin down dipole. It just means two opposite poles, right? Positive and negative charge in this case. Like a tiny magnet has north and south.
Precisely. For electric dipoles, it's a virtual electron-positron pair, for example. The positron positive gets pulled slightly closer to the central electron negative, and the virtual electron negative gets pushed slightly away. They align.
Ah, okay, so the vacuum sort of shields the electron's charge.
Exactly. It's called charge screening.
Yeah.
Because the virtual pairs align, the electron's charge looks weaker from far away than it does up close. This is experimentally confirmed. The total charge is zero, so conservation laws are fine. But the alignment has a real effect.
Okay, I follow that. So here comes the leap, right? Professor Hajdukovic's big idea.
Here it is. He proposes that gravity does the exact same thing, but, and this is the absolute linchpin, it relies on one huge assumption, that matter and antimatter have opposite gravitational charges.
Whoa.
Yeah.
Okay, so an electron falls down towards Earth, but an anti-electron, a positron, would fall up. It would be repelled.
That's the core premise. If that's true, then the quantum vacuum fluctuations aren't just energy pops, they're virtual gravitational dipoles. Matter has a positive gravitational charge, antimatter has negative.
So these pairs flickering in and out are like tiny gravitational plus-minus pairs, ready to be aligned.
Exactly. Ready to be polarized by a gravitational field.
Hold on, though. Let's pause right there, because this feels like a major hurdle. You just said electric fields have to be incredibly strong to polarize the vacuum, right? It only happens microscopically. But gravity is famously ridiculously weak, like the weakest force we know. How could gravity possibly be strong enough to align anything in that chaotic quantum vacuum? Isn't that a fatal flaw?
You'd think so, wouldn't you? But that's the beautiful twist, the counterintuitive part.
Yeah.
It's because gravity is so weak that the effect becomes macroscopic, not microscopic.
How does that work?
Think about it. Electric fields are strong, but usually localized. You need immense field strength near a particle to get that tiny QED polarization halo. Gravity, though weak, is long-range and pervasive. Every bit of matter contributes. So while the force on any single virtual dipole is minuscule, the collective effect of a huge, spread-out gravitational field, like from a whole galaxy, can gently nudge these virtual gravitational dipoles over vast distances. The weakness allows it to act coherently on a huge scale.
So instead of a tiny halo around one particle, you get a giant halo around an entire galaxy.
Precisely. This one-mechanism gravitational polarization of the quantum vacuum has both local consequences within galaxies and global consequences for the whole universe.
Okay, let's tackle the local first. Dark matter. The claim here is dark matter particles just don't exist.
Correct. The theory says what astronomers observe as the gravitational effect of dark matter is actually the gravitational field generated by this local polarization of the quantum vacuum. It's an enormous invisible halo of aligned gravitational dipoles surrounding the visible matter of the galaxy.
So the galaxy itself creates its own dark matter halo, in a sense, by polarizing the vacuum it sits in.
Exactly that. The stars, the gas, all the normal matter creates a combined gravitational field. This field immerses the galaxy in the QV ocean, and over time, it forces these virtual gravitational dipoles to align just a little bit. This alignment changes the vacuum from being gravitationally inert to being an active source of gravity itself.
It's like the galaxy is dragging the vacuum along with it, making the vacuum itself heavier, gravitationally speaking.
That's a great way to put it, yes. The vacuum gains gravitational weight where it's polarized.
Okay, conceptually elegant, but physics demands numbers. Does this vacuum wake idea actually match what we see? Does it explain galaxy rotation curves, for instance?
This is where it gets really compelling, maybe the mic drop moment of the theory, as the source material suggests. Astronomers found something really weird, empirically, just by looking at galaxies.
What's that?
If you measure the amount of dark matter mass inside a certain radius in a galaxy, and you divide that mass by the surface area of that sphere, so mass divided by 4
Okay, like a density, but over an area. A surface density.
Exactly. That surface density turns out to be nearly constant in the central regions of all types of galaxies. Spiral, elliptical, dwarf. It's always around the same value.
Huh. That doesn't sound like a coincidence. That sounds like some kind of fundamental limit or property.
Precisely. And in Hajdukovic's theory, this empirically observed constant value is interpreted as a fundamental property of the quantum vacuum itself. It's the maximum possible magnitude of the gravitational polarization density. Let's call it PG max.
Wait, let me wrap my head around this. You're saying the rotation speed of stars in a giant galaxy is ultimately limited because the quantum vacuum itself, the sea of virtual particles, can only be stretched or polarized so much before it hits a saturation point.
That's exactly the idea. The vacuum has a maximum gravitational polarization at PG max. It can't contribute more gravity beyond that point, no matter how much normal matter you pile in the center.
Okay, that's pretty wild. But how do we know this PG max value makes sense?
Here's the truly astonishing connection. This value, PG max, derived from looking at huge galaxies, is mathematically linked, through the physics of the theory, to a fundamental microscopic quantity.
Which is?
The mass of a specific fundamental particle. In the papers, it's closely related to the mass of the neutral pion.
Hold on, a pion. You're telling me the dynamics of a galaxy millions of light years across depends on the mass of a tiny, unstable particle like the pion. That sounds... I mean, is that just numerology? A coincidence? Why a pion?
It's not arbitrary. The reasoning is that the pion's mass, like the mass of protons and neutrons, is thought to arise fundamentally from the interactions within the quantum vacuum itself, particularly the QCD vacuum related to quarks and gluons.
Okay. So if the QV's inherent energy structure sets the maximum polarization, PG max, and that same QV structure also sets the masses of particles like the pion, then those two values have to be related.
Exactly. They're two macroscopic consequences of the same underlying microscopic reality, and the numbers work out. The observed astronomical surface density, roughly 0.06 kilograms per square meter, is compatible with the theoretical estimate for PG max based on particle physics constants like the pion mass. It connects the micro and macro scales in a really profound way.
Okay, that is compelling, especially when you compare it to the alternatives. Dark matter needs new, undiscovered particles. MOND, modified Newtonian dynamics, needs us to just change the law of gravity in weird ways when acceleration gets low without really explaining why.
Right. This proposal says no new particles, no changing fundamental laws, just account for the gravity of the polarized quantum vacuum using principles we already kind of understand from electromagnetism. And bonus, it naturally reproduces the MOND acceleration scale without putting it in by hand.
So it explains the galaxy observations using existing physics concepts, just applied to gravity and the vacuum. Okay,
Right.
that covers the local picture, the dark matter halo. Let's zoom out. What about the global mystery dark energy?
Right, the accelerating expansion. Dark energy is usually thought of as some kind of fluid with negative pressure pushing the universe apart faster and faster.
How does the local polarization halo idea scale up to explain that?
Well, the theory connects them beautifully. Think about all these galaxies across the cosmos, each one polarizing the quantum vacuum around it, creating its own halo.
Yeah.
Globally, this network of polarized QV halos acts like a cosmological fluid filling space.
Okay, a fluid made of polarized vacuum.
Yep, and here's the key. The effective gravitational charge, or energy density, of this QV fluid isn't constant. It actually increases as the universe expands,
Why does it increase?
because the individual galactic halos are still growing. As the universe expands, galaxies get more room gravitationally. Their polarization halos expand outwards until they eventually hit that maximum saturation limit, that PG max we talked about.
So as space stretches, the halos fill that space, adding more total polarized vacuum energy to the universe.
Exactly. And this has a huge consequence in general relativity. Normally, if you expand a container holding a fluid, the total energy either stays the same or goes down due to density decreasing. But think about this QV fluid. As the volume of the universe increases, the total energy stored in these growing halos also increases.
Right, because the halos are getting bigger.
In GR, if a component's total energy increases as the volume it occupies increases, that component mathematically must have negative pressure.
Okay, I think I follow. It's like stretching a rubber band. The more you stretch it, increase volume, the more energy it stores and it pulls back.
Yeah,
Negative pressure.
that's a decent analogy. This negative pressure, generated by the collective growth of all these QV halos, is what drives the accelerated expansion. The growth of the galactic vacuum wakes is the dark energy effect.
That's incredibly elegant. It unifies dark matter and dark energy into one phenomenon, the gravitational polarization of the quantum vacuum.
It really is, and the model predicts this negative pressure isn't constant. It starts high, driving acceleration, but then it gradually decreases as more and more halos reach their maximum size, their PG max limit.
And what happens when they all, or mostly all, hit that limit?
Once the halos are saturated, the total energy of the QV fluid stops increasing significantly with expansion. The negative pressure drops to nearly zero. And crucially, the accelerated expansion ends.
Wow. So unlike the standard lambda CDM model, which predicts eternal acceleration, maybe leading to a big rip, this theory predicts the acceleration is temporary.
Exactly. It naturally provides an off switch for dark energy, preventing a runaway universe.
Okay, and the sources also mention this framework deals with the Big Bang singularity problem too, suggesting a cyclic universe.
Yes, this is where the matter-antimatter gravitational repulsion becomes absolutely crucial. Imagine the universe collapsing back on itself in a potential big crunch.
Standard GR says that leads to an infinite density singularity.
But not here. As the collapse intensifies, the gravitational field becomes unbelievably strong. Strong enough, the theory proposes, to trigger the gravitational version of something called the Schwinger mechanism.
Which,
It's the process where an extremely strong field can basically boil the vacuum, ripping virtual antiparticle pairs into becoming real particles. An incredibly strong gravitational field would create huge amounts of matter and antimatter directly from the vacuum energy.
And crucially, if matter and antimatter gravitationally repel each other,
They fly apart violently. The collapsing matter gets converted into this exploding fireball of mutually repulsive matter and antimatter. It prevents the singularity from ever forming. The big crunch effectively bounces, converting the collapsing matter energy into ejected antimatter energy, initiating a new expansion phase, a new Big Bang.
so a cycle. Our matter-dominated universe came from the collapse of a previous antimatter-dominated universe, and the next cycle might be antimatter again.
That's the picture it paints. It avoids the singularity and also naturally explains the matter-antimatter asymmetry we live in, the matter half of the cycle. It also removes the need for that ad hoc inflation field to explain the early universe's smoothness, because the bounce mechanism itself might handle that. Okay, this is a remarkably coherent picture. One single core idea, gravitational dipoles in the vacuum, due to matter-antimatter repulsion, seems to potentially resolve 5 of the biggest problems in cosmology. But it all hinges on that core assumption, right? Does antimatter actually fall up?
That is the absolute bedrock, and its verification rests on 2 main pillars of experimental and observational evidence. Pillar 1, directly test the gravitational behavior of antimatter.
Which, thankfully, is actually happening right now at CERN.
Indeed. Experiments like ALPHA, AG, and G-bar are working incredibly hard, using sophisticated techniques to trap antihydrogen atoms made of an antiproton and an anti-electron or positron and directly measure how they fall in Earth's gravitational field.
So if they measure antihydrogen accelerating upwards, away from Earth,
It would be revolutionary, perhaps the biggest physics discovery in a century. It would prove the foundational assumption of this theory, that gravitational charge depends on matter-antimatter type, and that the weak equivalence principle of general relativity doesn't apply universally. Okay, that's pillar 1, the CERN experiments. What's pillar 2?
Pillar 2 is astronomical confirmation. We need to detect the subtle, constant gravitational acceleration predicted to be caused by that saturated, polarized quantum vacuum halo, that PG max effect we discussed earlier.
The effect that mimics dark matter locally. Where can we possibly hope to measure such a tiny, constant acceleration amidst all the gravitational noise of the solar system?
We need to go somewhere extremely quiet, gravitationally speaking. The proposal is to look way out in the far reaches of the solar system, at tiny binary objects orbiting each other beyond trans-Neptunian binaries. Objects like, say, 2002 UX25 and its small moon.
Why out there? What makes them special?
Because they are so far from the sun and so far from the giant planets, the normal Newtonian gravitational tugs from those bodies are incredibly weak. The internal gravity between the 2 small binary objects is also weak. This minimizes all of the standard gravitational noise.
Making it possible to potentially detect a much fainter, non-Newtonian signal.
Exactly. In that quiet environment, the constant tiny acceleration caused by the background polarized QV halo, the local PG max effect, might become the dominant non-Newtonian force acting on the binary's orbit.
And how would we see it?
It should cause a slow, steady drift in the orientation of the binary's orbit, something called perihelion precession, a measurable wobble that can't be explained by standard gravity from the sun, planets, or their mutual attraction alone.
And the numbers suggest this is actually detectable.
The calculations in the source material are quite promising. For a candidate like 2002 UX25, the precession predicted from this QV halo effect could be something like 27 times larger than the residual precession caused by the sun's gravity way out there. That's potentially a clear signal for powerful telescopes like the James Webb Space Telescope to find.
So we have concrete tests, both in the lab with antimatter and in the sky with distant asteroids. It's not just abstract theorizing.
Not at all. It makes specific, testable predictions. And it reinforces that idea mentioned in the sources, that spooky communication at a distance. The observation that seemingly unrelated microscopic constants, like pion mass, and macroscopic cosmological parameters, like dark matter density or the Hubble constant, appear numerically linked. This theory provides a potential physical mechanism why they might be linked through the properties of the quantum vacuum.
So let's try and sum this up for everyone listening. What we've explored today is a theory that offers really a breathtaking degree of unification. It takes one single, relatively simple hypothesis about the quantum vacuum.
The idea that it's made of virtual gravitational dipoles, because matter and antimatter repel gravitationally.
Right, and that one idea potentially replaces the need for 5 separate, complicated, and frankly kind of ad hoc fixes for the biggest problems in physics. Dark matter, dark energy, cosmic inflation, the cosmological constant disaster, and the matter-antimatter imbalance.
The scientific stakes here are just immense. We're really at a crossroads. Do we continue down the current path, which essentially requires us to believe the universe is filled with vast amounts of exotic, invisible stuff we haven't found and maybe can't ever find? Or do we need to adjust our fundamental common sense about gravity and empty space and embrace this counterintuitive but perhaps powerful reality of the quantum vacuum, as Professor Hajdukovic suggests?
It forces us to question basic assumptions. And that leads us to a final, maybe provocative thought to leave you with. If this theory is right, if the properties of the quantum vacuum may be linked to something as basic as the pion mass, define that gravitational saturation limit, PG max.
The limit that dictates galactic structure, essentially creating dark matter halos.
And if that same quantum vacuum structure, via particle masses like the proton, dictates the rules of chemistry and therefore the possibility of life.
Does that imply a deeper connection? Is the universe not just accidentally hospitable to life, but could it be that the very physics of the quantum vacuum fundamentally links the conditions needed for galaxies to form with the conditions needed for chemistry and life to emerge? Is life almost written into the structure of the vacuum itself?
Something to ponder. Are the constants just right by chance, or is there an underlying mechanism rooted in the vacuum ensuring that galaxies form and stars can cook up the elements for life? A lot to think about. Join us next time for another deep dive.
Thank you for listening. If you enjoyed this content, please consider subscribing and liking. Your support helps us continue to provide more free resources on advanced science and research. Until next time.